and night side. 91, 92. Surface features. Topography of the Moon measured from the Lunar Orbiter Laser Altimeter on the mission Lunar Reconnaissance Orbiter, referenced to a sphere of radius 1737.4 Euro-kilometer. Topography of the Moon. The topography of the Moon has been measured with laser altimetry and stereo image analysis. 93. Its most extensive topographic feature is the giant Farside South Pole Aitken Basin, some 2,240 kilometers, 1,390 mi, in diameter. The largest crater on the Moon and the second largest confirmed impact crater in the Solar System. 94, 95, at 13 kilometers, 8.1 mi, deep. Its floor is the lowest point on the surface of the Moon. 94, 96. The highest elevations of the Moon's surface are located directly to the northeast, which might have been thickened by the oblique formation impact of the South Pole Aitken Basin. 97. Other large impact basins such as Imbrium, Serenitatis, Chrysium, Smithii, and Orientale possess regionally low elevations and elevated rims. 94. The far side of the lunar surface is on average about 1.9 km, 1.2 mi, higher than that of the near side. 1. The discovery of fold-scarp cliffs suggests that the Moon has shrunk by about 90 meters, 300 feet, within the past billion years. 98. Similar shrinkage features exist on Mercury. Mare Frigoris, a basin near the North Pole long assumed to be geologically dead, has cracked and shifted. Since the Moon doesn't have tectonic plates, its tectonic activity is slow and cracks develop as it loses heat. 99. Volcanic features. The largest mare, the main dark region of the near side, is Oceanus Procellarum, with smaller mare, such as Imbrium and Serenitatis, that sit within its ring. Left of the centerline E Procellarum proper. The main features visible from Earth by the naked eye are dark and relatively featureless lunar plains called Maria, singular mare, Latin for seas, as they were once believed to be filled with water. 100. Are vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. 101. The majority of these lava deposits erupted or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria. 102. Almost all Maria are on the near side of the Moon, and cover 31% of the surface of the near side, 60, compared with 2% off far side. 103. This is likely due to a concentration of heat-producing elements under the crust on the near side, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt. 65, 104, 105. Most of the Moon's mare basalts erupted during the Imbrian period, 3.5 billion years ago, although some radiometrically dated samples are as old as 4.2 billion years. 106. As of 2003, crater counting studies of the youngest eruptions appeared to suggest they formed no earlier than 1.2 billion years ago. 107. In 2006, a study of Ina, a tiny depression in Lacus felicitatis, found jagged, relatively dust-free features that, because of the lack of erosion by infalling debris, appeared to be only 2 million years old. 108. Mooncakes and releases of gas indicate continued lunar activity. 108. Evidence of recent lunar volcanism has been identified at 70 irregular mare patches, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer because of the greater concentration of radioactive elements. 109, 110, 111, 112. Evidence has been found for two 10 million years old basaltic volcanism within the crater Lowell, 113, 114, inside the Orientale Basin. Some combination of an initially hotter mantle and local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities on the far side in the Orientale Basin. 115, 116. The lighter-colored regions of the Moon are called terra, or more commonly highlands, because they are higher than most maria. They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean. 106, 107. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. 117. The concentration of maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow velocity impact of a second moon of Earth a few tens of millions of years after the moon's formation. 118, 119. Alternatively, it may be a consequence of asymmetrical tidal heating when the moon was much closer to the Earth. 120. Impact craters. A grey, many-ridged surface from high above. The largest feature is a circular ringed structure with high-walled sides and a lower central peak. The entire surface out to the horizon is filled with similar structures that are smaller and overlapping. A lunar crater Daedalus on the Moon's far side. A major geologic process that has affected the Moon's surface is impact cratering. 121, with craters formed when asteroid-sound comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer, 0.6 mi, on the Moon's near side. 122. The lunar geologic timescale is based on the most prominent impact events, including Nectaris Imbrium and Orientale, structures characterized by multiple rings of uplifted material, between hundreds and thousands of kilometers in diameter and associated with a broad apron of ejecta deposits that form a regional stratigraphic horizon. 123. The lack of an atmosphere, weather, and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. 123. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment period of increased impacts. 124. High-resolution images from the Lunar Reconnaissance Orbiter in the 2010s show a contemporary crater production rate significantly higher than was previously estimated. A secondary cratering process caused by distal ejecta is thought to churn the top 2 centimeters of regolith on a timescale of 81,000 years. 125, 126. This rate is 100 times faster than the rate computed from models based solely on direct micrometeorite impacts. 127. Lunar swirls. A Lunar Reconnaissance Orbiter wide-angle camera image of the lunar swirl Rayner Gamma. Lunar swirls are enigmatic features found across the Moon's surface. They are characterized by a high albedo, appear optically immature, i.e. the optical characteristics of a relatively young regolith, and often have a sinuous shape. Their shape is often accentuated by low albedo regions that wind between the bright swirls. They are located in places with enhanced surface magnetic fields, and many are located at the antipodal point of major impacts. Well-known swirls include Rayner Gamma feature and Mare Ingenii. They are hypothesized to be areas that have been partially shielded from solar wind, resulting in slower space weathering. 128. Surface composition. Regolith. Blanketed on top of the Moon's crust is a highly comminuted, broken into ever smaller particles, and impact-guard needlessly gray surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. 129. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10-15 m, 33-49 feet, in the highlands and 4-5 m, 13-16 feet, in the Maria. 130. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. 131. Relative elemental composition of the lunar soil. Relative molecular composition of the lunar surface. 132. Compound formula composition. Maury Highland Silicato 245.4%, 45.5% alumina Al 20314.9%, 24.0% lime Cow 11.8%, 15.9% iron 2. Oxide Fio 14.1%, 5.9% magnesium Go 9.2%, 7.5% titanium dioxide TiO 23.9%, 0.6% sodium oxide Na2O 0.6%, 0.6% 99.9%, 100.0%. Presence of water. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly persist in cold permanently shadowed craters at either pole on the Moon. 133, 134. Computer simulations suggest that up to 14,000 km to 5,400 square mi of the surface may be in permanent shadow. 79. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. 135. In years since, signatures of water have been found to exist on the lunar surface. 136. In 1994, the bistatic radar experiment located on the Clementine spacecraft indicated the existence of small, frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from ion impact craters. 137. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. 138. Volcanic lava beads, brought back to Earth aboard Apollo 15, showed small amounts of water in the interior. 139. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice, using the onboard Moon Mineralogy Mapper. The spectrometer observed absorption lines common to hydroxyl in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1000 ppm. 140. Using the mapper's reflectance spectra, indirect lighting of areas in shadow confirmed water ice within 20 degrees latitude of both poles in 2018. 141. In 2009, LCROS sent a 2,300 kilograms, 5,100 pound, impactor into a permanently shadowed polar crater, and detected at least 100 kilogram, 220 pound, of water in a plume of ejected material. 142, 143. Another examination of the gross data showed the amount of detected water to be closer to 155 plus or minus 12 kilograms, 342 plus or minus 26 pound. 144. In May 2011, 615-1410 ppm water in melt inclusions in lunar sample 74,220 was reported. 145. The famous high titanium orange glass soil of volcanic origin collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this insight does not mean that water is easily available, since the sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ocean microprobe instrument. Analysis of the findings of the Moon Mineralogy Mapper, M3, revealed in August 2018 for the first time definitive evidence for water ice on the lunar surface. 146, 147. The data revealed the distinct reflective signatures of water ice, as opposed to dust and other reflective substances. 148. The ice deposits were found on the north and south poles, although it is more abundant in the south, where water is trapped in permanently shadowed craters and crevices, allowing it to persist as ice on the surface since they are shielded from the sun. 146, 148. In October 2020, astronomers reported detecting molecular water on the sunlit surface of the Moon by several independent spacecraft, including the Stratospheric Observatory for Infrared Astronomy, SOFIA. 149, 150, 151, 152. The geologic map of the Moon at 1-2.5 m scale by Chinese Academy of Sciences. See the original file for high-resolution. Earth-Moon system. Orbit. SCAFA satellite sees the Moon passing in front of Earth. The Earth and the Moon form the Earth-Moon system with the shared center of mass, or barycenter. This barycenter stays located at all times 1,700 kilometers, 1,100 mi, about a quarter of Earth's radius, beneath the Earth's surface, making the Moon seemingly orbit the Earth. The orbital eccentricity, giving ovalness of the orbit, is 0.055. The lunar distance, or the semi-major axis of the geocentric lunar orbit, is approximately 400,000 kilometers, which is 250,000 miles or 1.28 light seconds, and a unit half measure in astronomy. This is not to be confused with the instantaneous Earth-Moon distance, or distance to the Moon, the momentaneous distance from the center of Earth to the center of the Moon. The Moon makes a complete orbit around Earth with respect to the fixed stars, its sidereal period, about once every 27.3 days, However, because the Earth-Moon system moves at the same time in its orbit around the Sun, it takes slightly longer, 29.5 days winking sat smiley J, 60, to return at the same lunar phase, completing a full cycle, as seen from Earth. This synodic period, a synodic month, is commonly known as the lunar month and is equal to the length of the solar day on the Moon. 153. The Moon has, due to tidal knocking, a 1-1 spin orbit resonance, This rotation-orbit ratio makes the Moon's orbital periods round Earth equal to its corresponding rotation periods. This is the reason for only one side of the Moon, its so-called near side, being visible from Earth. That said, while the movement of the Moon is in resonance, it still is not without nuances such as libration, resulting in slight